When you start working on notes for this lesson, graphing square root functions and transformations, you need to know that HK, which is always an important point in the transformation formula, is called an endpoint. Also, you can use a step pattern if you like to, but it'll work a little differently than it did with quadratics, where we went right one and then up one, and then right one and then up three, and then right one and then up 5, if you remember that step pattern. This is the inverse of that, and it grows sideways faster than it grows up and down. So now we'll go up 1 and right 1, and up 1 and right 3, and up 1 and right 5, and up 1 and right 7. So it's the same step pattern, but instead of growing vertically with the steps, it grows horizontally with the steps, and it always grows to the right. If you don't want to use that, that's okay, but if you like the step pattern, that's how it works for these. And we will restrict the domain or the range so that when you do a square root calculation, you always get a positive number or 0. So I kind of touched on that with the warm-up activity, the discovery activity, which I also made a video for. So basically, the big idea here is that when you do a square root of anything, then whatever is in here must be 0 or more, so that you're taking a square root and you'll get a regular real number value. Let's look at the parent function for square root. I can choose x's and calculate y's, just like regular. I'm going to start at 0, 0, and here, if I choose x is 0, y would be square root of 0, which is 0. So 0, 0 is on my graph. And x is 1, y would be square root of 1. That's 1. So 1, 1 is on my graph. And I can do 2, and then it would be square root of 2, but that's not really easy to draw. It's a decimal. So if we just kind of skip through here to, I could do 3, and I have 3 and square root of 3. If I did 4, then y would be square root of 4, that's 2. So that's easy to graph, 4, 2. And the next perfect square, so that if I took a square root I would get a whole number, is 9. 9 is 3 squared. So 9, 3 is on this. And just like the step pattern, where you go up 1 over 1, up 1 over 3, up 1 over 5, you could make yourself a table using calculations. You could type the equation that you're wanting to graph into the calculator and look at a table. So you do you. The endpoint for the original square root function with no transformations is 0, 0. That's because when I draw this graph, this is the end. Here I have an arrow to the right, and to the left it ends right here, or it starts right there, either way. There's nothing to the left or below. My domain is 0 to infinity. My x's start at 0 and then increase. That includes 0, so I put a bracket there. My range is also 0 to infinity, but for a different reason. It's because the lowest place I have is 0, and then it grows vertically. So this is what we have. That's plain old square root of x with no decorations, no embellishments. Okay. Below this, you have the transformation equation. And A affects shape and direction, just like it did last semester. The direction change is if A depends on what the sign of A is. If A is a positive number, then your graph will be increasing. As x increases, y will also increase. So if I was walking on this curve, I would walk up the hill. If A is a negative number, then my graph will have a reflection. It'll be upside down. It still moves to the right. But because as x numbers increase, y numbers will decrease, we call this a decreasing function. H is in charge of horizontal shift, so sliding the endpoint right and left, horizontal shift. And K is in charge of vertical shift, so not vertical shape changes or vertical direction changes, but instead sliding the whole graph up and down, so shift. Your endpoint is H. Okay. So this is in general, this is true of everything. If A is a positive number, I'm not sure why it's capital here, but we usually write it with this lowercase a. If A is positive, as I said, your graph is increasing. Looks like this. So your domain will be describing all the x's that are graphed, starting at the end point and then going positive forever. So I could write h comma infinity, including h, whatever that number is for the domain. And the range, if my graph is increasing, you always describe range from lowest to highest. The lowest will be the y part of the vertex, which is k, and then the highest, I have an arrow here, so it'll just keep going up higher. So anytime your a number is positive, it's increasing, this is what your domain and range will look like. However, if a is negative, then you have a reflection. So your graph is upside down. Your domain still describes the end point, and then x will increase. So the domain will be the same, whether it's increasing or decreasing. But your range describes the graph from lowest to highest, and now the highest point is at the end point. So I would say the range is from negative infinity up to k, like this. There's a note on here for how to graph using the step pattern, and when I explain step pattern, I explained it just a little bit differently. The notes that are on here explain as you starting from the vertex each time to count. I go over 1 and up 1 for a quadratic, and then I go back to the vertex and I go over 2 and up 4, and I go back to the vertex and I go over 3 and up 3 squared, 9. But that's not how I explained it. I mean, this is valid if you go back to the vertex each time. Also, it's symmetrical over the axis of symmetry. When I explained step pattern for quadratics, what I said was from the vertex, which is your starting point, then I would go over 1 and up 1, and then I would stop at that point, or 1 times a, I'm sorry. And then I would go over to the right 1 more unit, and then up 3. I explained it like over 1, up. I keep forgetting just to do the 1, sorry. Over 1, up 1, over 1, up 3, over 1, up 5. So the stairs are increasing by the next odd count. And then it's reflected across x equals h. That's your axis of symmetry. The square root step pattern, this works fine if you go back to the end point before you're counting each time. If you want to count using odd numbers, like we did here, just know that it lays over to the side. So I will go up 1 and over 1, and I'll go up 1 and over 3, and up 1 and over 5. And these are all times a. 1 times a, 3 times a, 5 times a, 7 times a, as it did, but instead of the y growing so quickly, the x grows more quickly. I just did this backwards. That's why we do math in pencil. I told a fib. That is not what we do. Undo that, please. What changes? A is still a vertical change. So you have normally up 1 over 1, but we'll do up. A changes the up and down shape, or the up and down direction. So I'll do a times 1, and then over 1. And then I'll do up a times 1, and then over 3. And then I'll go up a times 1. So the vertical change will be consistent. The vertical change will be a each time, and the horizontal change will be odd numbers. So we won't change, this one was, we're changing the multiple with the odd numbers when we're increasing up and down, and this one we are changing the multiple when we increase up and down, but that is times a single unit. So if a is 2, I'll go up 2 and over 1, up 2 more and over 3, up 2 more and over 5. If a is a third, I'll go up 1/3 times 1 over 1, up 1/3 times 1 again over 3, up 1/3 times 1 over 5, or down 1 over 3, or whatever. Okay, sorry about that. But again, you don't have to use step pattern. You can type the equation in the calculator and make yourself a table. That works fine. Okay, I'm gonna talk you through 2 of these on the back side of your notes, and I'm going to leave 2 for you to do. So we've got some of these on your own, little guys, here, and you do those. I will scan these completed into Canvas so that you can check yourself, but try. I think you got this. You can do it. One type of equation that you'll have, or one type of problem that you'll have on your assignment, is you'll be given transformations with words compared to the original f of x equals square root of x function. Here it says write the new function that's transformed as g of x and identify the new endpoint. So I need to translate these descriptions into which variables are they for your transformation equation. So if I compare this to the transformation equation, which is typed on the other side of your page, y equals a square root x minus h plus k, then I just need to know which one of these descriptions is a and which one is h and which one is k. I have a vertical stretch by 3/2. It's a stretch because 3/2 is 1.5, so it's bigger than 1. Stretch is an a thing because it changes the shape. So I can say a is 3/2. It doesn't say anything about h. So h is 0 because it doesn't say that your graph slides right and left. No horizontal changes. And k is 7 because your graph moves up 7. So then I substitute these into your transformation equation, and I'll write it as g of x, that's in the instructions. G of x equals 3/2, I wrote 3/3, silly person. Square root x minus 0. You could put just square root of x and not put that in there, but this is the same, plus 7. H goes inside the radical with the x. K goes outside. Be really careful when you type this into a calculator. If you want to type into the calculator and check yourself, you could graph this and look at it compared to square root of x and make sure that you would describe it this way. And hopefully you would. Endpoint is hk, so my endpoint is at 0, 7. And you do this one. Then you have identify the endpoint, the domain, the range, the transformations. So this is all the critical elements. Also, whether it's increasing or decreasing, I believe, is part of your assignment. Maybe, and provide a graph. I'm going to, when I do these, I'm also going to graph the original square root of x function. And I'm using the step pattern, but hopefully it'll just get familiar to you kind of how it goes, or you could type it into a calculator and look. If x is 4, y is square root of 4, that's 2. If x is 9, y is square root of 9, that's 3. So this is what we're comparing to here. And you don't have to draw this on yours, but it might be good for a couple of them just so that you can compare This is what square root of x looks like. But I need to graph and describe 2 square root x minus 1 plus 3. And when I compare this to the transformation equation, I would say a is 2, which changes the shape of my graph. I have a vertical stretch. My graph will be 2 times as tall as this graph. So instead of going up 1 step, every time I move horizontally to the right, I'll go up 2 steps every time I move horizontally to the right. H is 1. So my graph, the end point, slides 1 block to the right. Horizontal, oops, shift, right, 1 block, and K is 3. So I also have a vertical shift up 3 units. My endpoint is HK. So my endpoint is at 3 here. And the step pattern will be up 2 times 1, because it's always a times 1, and then right 1, and then it'll be up 2, right 3, and then I'll go up 2, right 5, and so on. You're also welcome to make yourself a table here instead of using space to make a step pattern. You could type this into a calculator and provide yourself a table to do the graph. Here I'm going to go up 2 and over 1, up 2 and over 1, 2, 3, up 2 and over 1, 2, 3, 4, 5. So my graph looks like this. The domain is all of the x's that I just graphed here, and those include x's beginning at 1 and then getting larger and larger to infinity, including 1, so I use a square bracket. The range is this graph from the bottom to the top, and the lowest place is at 3k. So my graph goes from 3 to infinity, closed bracket on the 3. It is increasing, just by the way, because a is positive. Okay, and there's one for you to do on your own. And just like that example at the top of this side of the page, I'll have it scanned on Canvas so that you can check yourself. But go ahead and work through it on your own or with your table. You got this.